Geometry for three, geometry for three. That's one hot math. Geometry for three.
Hello, fellow mathematicians, and welcome to Geometry for Three, where we sit down with two of history's best mathematicians and discuss their life, their math, and their legacy. We have an exciting show in store for you today. We are joined by the reincarnated Bernhard Riemann, followed by the always interesting Pythagoras. Our first guest is well renowned for introducing the novel concept of a curvature in two-dimensional region. You all know who I'm talking about. Come on down, Bernhard Riemann.
Hi.
Hello, Bernhard. Welcome to Geometry for Three. I love your work with math and geometry. You're so smart. So you grew up in Germany during the 1900s. What was that like?
Oh, you know.
Oh, yes, I can imagine it was just like the 1990s. I loved that time period. Anyways, you were the second of 6 children. What was that? What was your family?
Well, as you said, I was the second oldest of 6 kids. I was always a nervous child, which was probably attributed to the early death of my mother. My father was a Lutheran pastor who fought in the Napoleonic Wars, so we were rather poor, but I always had math to get me through.
Yes, everyone knows you were a math prodigy, but not everyone is aware that you also studied the Bible.
Yeah, my father was a pastor, so I always studied religion too. But my religious studies were definitely not as interesting as my math. Math always came sort of naturally to me.
I understand. It comes naturally to me too. I'm super good with addition. Anyway, enough about me. So you went to go study in many German universities, but you were always plagued by illness. How did that affect you?
Well, as I said, my mother was killed by tuberculosis, and it took my brothers and sisters too. In 1866, I died from tuberculosis.
Oh my god, that story is so sad and heart-wrenching. Maybe we should segue into your career as a mathematician. Would you like to explain the discoveries to the audience?
I developed the mathematical idea that a summation of a large number of small parts of a region can be used to define the integration operation. Although this was not the first discovery of how to find the area under a curve, it is the method most frequently used to make this easy.
What?
You can find the area under a curve by breaking down the curve into small area elements, approximating the area of each of the elements, and adding them together. The more area elements that you have, the closer you will get to finding the real area under the curve.
I think our studio audience might need a few examples of your work.
I suppose I can. Okay. Let yt represent the population of Stoughton over 12 years, where y is a differentiable function of time t. The table shows the population at every 3 years. So these numbers will represent the y-axis. They will be shown on the y-axis. And years would be on the x-axis. So to find a left-hand Riemann sum,
Oh, he loves
you take this number, the number on the left. So 118.
Oh, look at Klausy.
8 times the difference between these numbers, so 3.
He doesn't agree. Klaus, it's right.
Okay, and then you keep doing it, finding, these will represent rectangles, so there will be 1, 2, 3, 4 different rectangles, and you take that number times the difference in the numbers on the top. So 12 to 90 times 3, 12, 4, 13 times 3, and 13, 174 times 3 to find the number of people. So this will be 35, 664, 36, 870, 37, 239, and 39, 522. So then you add all of these up.
To get the total people that lived in the town.
Yeah. 149, 295.
And to find the average population, you would...
You would divide this by the total number of years, which is 12. So divide that number by 12. And you get 12,441.25. But you can't have a fourth of a person. So it would be about...
You can't?
You can try. It'll be about 12,441 for every year.
Oh, okay. And how would this number be different if we used a right Riemann sum?
This number will be an underestimation of the total number because it will not include some of the area under the curve.
Mm-hmm.
So it'll be under the real number.
Okay.
Yep. Would you like me to show you a right hand?
I think I'd better see one.
Okay. All right. Let me erase this here with this scrunchie. Okay. So to do a right-hand Riemann sum, you do the same thing, except you do it from the right side. So instead of using this number, you'll use this number.
Oh.
For
so
the
the height
number.
of the rectangles are different.
Yeah. Yeah, you're
Got
going
it.
from the other side. So for this one, it'll be 12,290 times 3. 12,413 times 3. 13,174 times 3. And 13,945 times 3. So for these, you'll get 36,870, 37,239, 39,522, and 41,835. So when you add all of these up to find the total number of people, you'll get 155,466, which will be bigger than the other number.
Yeah, it is.
Yeah. And when you divide this by 12, you'll get 12955.9, which, as you can see, is...
Can't have a ninth of a person.
Yeah, you might want to round that one up, though, because it's 0.9.
Oh.
So for this one, you can see it's a lot bigger than the number for the left-hand Riemann sum, because it's including area that is outside of the curve. Yeah. So, do you need...
How would midpoint Riemann sum affect this?
Do you want me to show you?
I would like that very much.
Okay, I can do that. Hold on a second.
1,000.
No. Time was different in the 1800s. Okay, so for midpoint, we're just going to separate it into two different triangles. So we're going to do it from...
Rectangles?
Yes, rectangles. Those things. Geometry was different in the 1800s too. And so we're going to do it from here to here and here to here, using these numbers in the middle as the midpoint.
Yeah. Gotcha.
So we're going to multiply 12,290 by 6 this time.
Wow, changing it up.
Yeah, because it's a bigger difference between these numbers. And 13,174 times 6.
Oh.
So when you multiply these together, it'll be 73,740 and 79,044. Add these up, you get 152,784. And divide that by 12, you get 12. 12.
Numbers different too.
Yeah, you know it. 12,732, which will be between the two and be
Yeah.
closest to the actual approximation of
Well-
the area under the curve.
Thank you for being on our show, Bernard.
You're welcome.
Everyone give him a... Oh.
Thanks.